In this submodule, we'll develop a neat trick for computing certain types of derivatives. It's called L'Hopital's rule, after a French mathematician who was the first to put this in writing, though it's debated whether he actually discovered it or not. So the motivation is that we've seen already that certain quantities are not well defined. Things like 0 over 0, infinity over infinity, which can come out especially from certain limits. For example, we saw in submodule 1.4 that sine of x over x as x tends towards 0 is equal to 1. But direct evaluation, that is, if I simply try to plug in 0 in all the places for x, this yields 0 over 0, which is bad. So these types of limit problems are what we're referring to in this submodule. So the technique of L'Hopital's rule gives us a way to potentially solve these types of limits in a relatively straightforward way. So we'll be looking at limits of the form x goes to y of f of x over g of x when direct substitution would yield an indeterminate form, like 0 over 0 or infinity over infinity. So in these special cases, we can perform manipulations, of course, to f of x and g of x. So these could be things like factoring. We could try and factor out the thing that's giving us the 0 in both the top and the bottom. We could do some geometry, which is what you would do to directly prove that the limit as x goes to 0 sine of x over x is 1. But there is an alternative trick. Now, it's often abused by calculus students. So I'm going to warn you, you have to be careful when using it. But when it works, it makes these limits super easy. So what it says is, well, L'Hopital's rule says, if the limit as x goes to y of f of x equals the limit as x goes to y of g of x equals 0, so if they're both 0 or both infinity, then if I want to evaluate this, which will be indeterminate, 0 over 0 or infinity over infinity, something I can do instead is simply differentiate f and differentiate g and then take the limit of that ratio. So essentially what it says is when I have the indeterminate form 0 over 0 or infinity over infinity, I can replace f with f prime and g with g prime, and then try to recompute the limit. In some cases, it'll be easier to compute the limit with the derivatives than without them, which is why this is such a useful rule. So one remark is that what we're not doing, we are not taking the derivative of f over g. To do that, we would have to have the quotient rule. Here, we're just taking f prime over g prime. So maybe this is what you would fantasize the quotient rule telling you to do. That if I wanted to take the derivative of a quotient, I would simply take the derivative of the numerator, divide by the derivative of the denominator, and be done. We know that's not how you do it. But for L'Hopital's rule, it does work that simply. So let's look at some examples. Compute the limit as x goes to infinity of x plus 1 divided by 3x minus 1. So let's try direct substitution. I get infinity plus 1 over 3 times infinity minus 1. So infinity over infinity. So I get an indeterminate form. So only after checking this can you use L'Hopital's rule. I got infinity over infinity. So L'Hopital's rule applies. So I can compute the limit as x goes to infinity of x plus 1 over 3x minus 1 is equal to the limit as x goes to infinity of x plus 1 prime over 3x minus 1 prime. So this is 1 over 3, so 1/3. Now, there are other ways we could have gotten this limit. We could have done some algebra on the original equation and gotten 1/3. But L'Hopital's rule is very, very simple, as you can see. So let's look at another one. We're going to compute the limit as x goes to 0 of e to the x minus 1 over x. So let's check if direct evaluation gives us what we need. So if I evaluate x equals 0, I get e to the 0 minus 1 divided by 0. So 1 minus 1 over 0, so 0 over 0, which is indeterminate. So I'm in a situation where L'Hopital's rule applies. So the limit as x goes to 0 of e to the x minus 1 over x. I'll differentiate the top and the bottom. And what do I get? Well, the derivative of e to the x is e to the x, and the derivative of x is 1. So I get the limit as x goes to 0 of e to the x, which is 1. Not too bad. So in this case, was there another way to see what this limit should be? Yes. Right? So I'll just make a remark. This is the limit definition of the derivative of e to the x at x equals 0. So if you go back and look at the limit definition of the derivative, you'll see that what we're doing here is differentiating e to the x at x equals 0, which of course is 1. So let's look at this. Limit as x goes to 2 of x to the 3 minus 8 over x minus 2. So we try substitution. And I get 2 cubed minus 8 divided by x, 2 minus 2. So 8 minus 8 over 2 minus 2, which is 0 over 0, so indeterminate. Again, I ended up with an indeterminate form, so I can use L'Hopital's rule. So I differentiate top and bottom. And I just get the limit as x goes to 2 of 3x squared. So 3 times 4, which is 12. Now another way we could have gotten this was to factor the top and the bottom. The top would factor as x minus 2 times some quadratic, and we could have canceled out the x minus 2 on the top and the bottom. But again, L'Hopital's rule gives us another way to do this. So let's look at one more that we've already seen. Limit as x goes to 0 of sine x over x. So if I do a direct evaluation, I get sine of 0 over 0, so 0 over 0. Right? We already know that this is indeterminate. So by L'Hopital's rule, if we didn't already know that this was 1, we could differentiate and say that I get cosine x and 1 cosine is continuous, so I just get cosine of 0, so 1. Right, so we can see that L'Hopital's rule is really a very powerful technique for us. But we have to be careful. So here's a similar looking one. I have a trig function divided by a polynomial. But I need to check that I can actually apply L'Hopital's rule. It certainly looks like I can, because it looks so similar to sine x over x. But let's see what happens when we actually evaluate at x equals 0. I get cosine of 0 over 0, which is 1 over 0. So this is not indeterminate. So I cannot use L'Hopital's rule. So we need to do some more sophisticated analysis. So I'll say note, from the right, we get plus infinity, and from the left, get minus infinity. So this does not exist. So one might be tempted to say, apply L'Hopital's rule, evaluate, and get that the limit is 0. But that doesn't work here. We actually do not have an indeterminate form. We have 1 over 0, which is something, which is like infinity or negative infinity, depending on the sign of, how the sign of the term that's going towards 0. So this is sort of a trick, right? And this is why I say you have to be careful with L'Hopital's rule. It's very tempting whenever you have a ratio and you have to take a limit and you get something weird to do L'Hopital's rule. But the only weird things you can do with L'Hopital are the indeterminate forms, like infinity over infinity and 0 over 0. So use this tool, practice with it, but understand it has natural limitations. And these limitations are something the CLEP exam likes to test. They like to see if you actually understand the rule or you just use it indiscriminately. So practice, and it'll be very useful for you.